Okay, so we spent a lot of time talking about entropy, entropy for a system, entropy for the surroundings, entropy for the universe. They all give a little bit of different information. What we're going to discuss now is Gibbs energy, okay? And so it takes everything that we've done before, which you definitely still need to know how to do, and it simplifies things down. We're going to focus on one thermodynamic quantity, all right, that gives us second law information directly, okay? So the thing to realize about Gibbs energy, like the important thing about it, is that it gives us, sorry about that, it gives us spontaneity. Okay, so instead of having to calculate separately what delta S for the for the system is, and then delta S for the surroundings to get delta S for the universe, it just does that all at once. Okay, what we say and what's happening in the background is that it maps onto the second law, which makes sense because the second law gives spontaneity. It does so for isobaric and isothermal processes. Okay, so that's an important detail to know. We don't really explore it this semester, but it's done when we have a constant pressure and a constant temperature. That's when Gibbs energy matters, and in physical chemistry we explore that idea more. But for us this semester, spontaneity, okay? It has a different sign convention though than delta S of the universe, okay? When delta G is negative, then we have it as being spontaneous as written. So a negative delta G says, hey, whatever we have written, it's gonna happen, okay? When delta G is 0, we're at equilibrium. So then there's no net motion from the left to the right or right to left. When delta G is positive, okay, it's not spontaneous as written, and the reverse is spontaneous. So it has a different sign convention, okay? Negative spontaneous, right, left to right. Delta G is 0, you're at equilibrium. When it's positive, the reverse is spontaneous. Okay, so we can see that delta G, just like delta SU, and it is mapping onto it, but delta G is going to play a role in like K versus Q, right? Which is another way that we decided which way things were going to move. Delta G, Gibbs energy, is a state function. So we see this normal state function relationship that we can come up with tabulated information. This is on a table, this is on a table. You do this for the products, you do it for the reactants. We've seen this before. When we do this with delta H, there's one main difference here. When we do this with delta H, that's delta H naught for all temperatures. When we do this for delta S, and these are S's on the inside, that's delta S naught for all temperatures. This semester, remember, we assume that delta H naught and delta S naught, once you know them for all temperatures. When you do this for the table, right, with delta G naught, that's only for 25 degrees Celsius, because that's the temperature of that table. What we'll find is that delta G does change with temperature. So we pretend that delta H doesn't, we pretend that delta S doesn't. But delta G definitely changes with temperature, and that makes sense because things change their spontaneity based off of temperature. And we kind of even saw that with Le Chatelier's principle in terms of moving the equilibrium around if we increase temperature for an exothermic reaction or decrease temperature for an exothermic reaction, so on and so forth. So the big difference here is, yep, you can do the exact same calculation you can do for those other thermodynamic quantities, but this is only valid at 25 degrees Celsius. If you do it and you're analyzing a problem at 25 degrees Celsius and you get a delta G reaction naught that's negative, that tells you that under standard conditions, it's spontaneous. If you use this calculation and you get a 0 out, that means that under standard conditions at equilibrium. If you do this at 25 degrees Celsius and you analyze it and you get a positive value, then that means under standard conditions you have a situation, all right, where the reverse process is spontaneous, all right? So it's a different sign convention we need to be able to gather up and be able to use, right? But it's not too bad. So what do we use when we're talking about reactions away from your table temperature? All right, that's the first place we're going to start. So how do we get delta G naught? So still underneath, still at standard conditions, but at a different temperature. So at a temperature that's not at our table temperature, not at 25 degrees Celsius. There's a very important equation. Delta G naught is delta H naught minus T delta S naught. Okay, so this relationship applies for all temperatures. Remember what we said before, and I'm going to reiterate it one more time because it's how we approach problems and it's what we have to know. This I can get from a table, right? I could put a subscript reaction here if I need to, right? And then I could get delta H naught for your reaction. Same thing for delta S naught for your reaction. Can get that from a table. But what if this T is not 25 degrees Celsius? This I know, this I know, this I can calculate by putting in a temperature there, okay? Now what we can do is we can also analyze at standard conditions, right? And then we're going to do an example of how to use this mathematically in a little bit. But what I'm going to show you now is something that's important here, all right? So what we're going to do underneath here is we're going to draw out a sign convention. I'm going to label this delta H naught, delta S naught, all right? And then I'm going to put delta G naught over here. Because there's some important things we have to realize about how these guys interrelate. Remember, for a reaction, right, to be spontaneous as written, this has to be negative, okay? Well, if I have an exothermic reaction, delta H is negative. If at the same time, the disorder of my reaction is increasing, if I analyze this up here, I have an exothermic reaction, so that's negative. My disorder is increasing, so that's positive, but there's a negative sign there. Then no matter what I do with temperature, if delta H naught is negative and delta S naught is positive, right? For these situations where we have an exothermic reaction and entropy is increasing, right? Disorder is increasing, delta G is always negative. Now, why is that important to know? That means that no matter the temperature, okay, I'll always have a spontaneous reaction, right? No matter what. Right? What happens if I have an endothermic reaction? Well, then this is positive, right? What happens if at the same time, all right, I have a decrease in disorder, so I have a more ordered reaction? When this is positive and this is negative, this is positive. The negative here and the negative here make this positive. A positive plus a positive gives me a positive delta G every single time. Okay? Now, why is that important to know? Because if this is endothermic and my disorder is decreasing, right, my reaction will not be spontaneous no matter the temperature. And in fact, the reverse is spontaneous no matter what. Okay? Real important idea is just analyzing in terms of sign convention. What happens though if we change this up? And this is where temperature effects become really important. What happens if I have an exothermic reaction, but I have a decrease in disorder? Well, this is negative, but this term is positive. Because if I put a negative sign in there, this becomes a negative times a negative, a positive value. So a negative and a positive, we can't make any drastic assumptions about what delta G naught will be. And in fact, that's when temperature becomes a major control of spontaneity. Same thing if this is endothermic, okay? If this is endothermic, and this shows an increase in disorder. If this is positive, and I put a positive value here, this is negative, oh, I have a positive number here and a totally negative number there. We can't say what delta G is going to be until we analyze temperature. So there are 4 different conditions here. The first 2 we wrote down, we knew what delta G naught was going to be every single time, no matter the temperature. These last 2 are more interesting in a lot of ways because we won't know what delta G naught is until we tackle that temperature. And why is that sign important? Because that tells us under standard conditions whether we have a spontaneous process or a non-spontaneous process. Okay, so know how to do that analysis. That's a common analysis too that shows up on standardized exams a lot. Let's actually put some math to this. Let's do a quick little example here. Let's say we have this reaction A, which is in its gas form, to B in its gas form. And let's say that we analyze this and we look at table information, and what we find out is delta H naught is 500 joules per mole Kelvin. And we figure out that delta S naught is equal to 1.29 joules per mole Kelvin. So this is information that we could get from a table or it could be given to us in a problem. And now what we can ask ourselves is, all right, under standard conditions, at what temperature will the reaction become spontaneous? Under standard conditions, at what temperature will the reaction become spontaneous? Okay. Well, now we could go through the process of figuring out delta S and delta S for the surroundings, put them together to get delta SU, or what we're learning now is if we're given this freedom, if I know delta H naught and I know delta S naught, then I can get delta G naught, and that will give me spontaneity directly, okay? So what I want to know is, when will the reaction become spontaneous? We have a situation where we have an endothermic reaction, so that's positive. Oh, and we have an increase in disorder because this is positive, so this is negative. So we have one of those important situations where T matters. So here's how you're going to approach this problem. You're going to write this down, okay? And then what you're going to do is you're going to say, okay, I want to figure out the temperature where it's at equilibrium first. So what you do is you figure out where this reaction is going to be at equilibrium, and then you know from there, if you look at the math, any temperature that's higher than that is going to make this negative. Okay, so if I find out where these guys are equal, okay, then I know if I can make this more negative by increasing temperature, my delta G won't be 0 anymore. It'll be negative and spontaneous, right? So that's the thought process. You do the sign analysis and you say, okay, let's figure out where it's at equilibrium, and then what do I have to do with the temperature to make it negative, right? So let's throw these numbers in here. So what we have with this example is 0 is equal to 500 joules per mole Kelvin minus T times 1.29 joules per mole Kelvin. Right. When I do this math, I get a T that is 388 Kelvin. This is the temperature for equilibrium. So then my answer is any T greater than 388 Kelvin will produce a negative over here. 388 produces a 0. That's what we're showing here. But any T that's greater, I can throw in there, and then this sum is going to be a negative value, delta H minus T delta S naught, right? So when T is greater than 388 Kelvin, then we know that delta G naught is negative. We're analyzing standard conditions, okay? So then we're at a situation where we know it's going to be spontaneous, A going to B, right? A going to B, right? Pretty simple idea, but it's important to kind of stay organized with things. So another important thing that we have to realize with delta G naught, right? Besides how to look at the sign in this reaction, in this equation. Look at the signs in this equation, be able to see what the sign of delta G naught is, right? To be able to predict spontaneity under standard conditions, just based off the sign. The big important thing about delta G naught is that, yep, it gives spontaneity under standard conditions, but delta G naught info can give K. Delta G info can give you your equilibrium constant. Really, really important idea, okay? Delta G naught is equal to minus RT, the natural log of K. And we can rearrange this, and we can solve for K. The equilibrium constant for a reaction is equal to minus delta G naught over RT. We're going to use our energy R, our 8.315, and as always, our T is definitely in Kelvin. So delta G naught, not only does it give us spontaneity under standard conditions, but it gives us a way of calculating our equilibrium constant. All right. This is really kind of cool and like incredibly powerful idea. All right. So let's go back to our example. All right. And let's say, okay, at 300 Kelvin, all right, for the reaction A going to B, all right, what is K? All right, what is our equilibrium constant? So then here's our thought process, right? What I need is an equation that gives me K, where I can use thermodynamic information to get a numerical value. So that's going to be our equation that we're going to use there. So what I need is, delta G naught is the main component up there. I know what T is, I know what R is, so I got to figure out what delta G naught is. 300 Kelvin is not directly from a table, all right? It's not our 25 degrees Celsius information. So I'm going to have to use delta H naught minus T delta S naught. Well, in our previous example, we gave delta H naught and we gave delta S naught as values. And once you have those values, remember that those values are set no matter the temperature, okay? So what I can do is I can take my information, this was 500 joules per mole Kelvin, right? This delta H naught, right, is going to be at 300 Kelvin, and our delta S naught was 1.29 joules per mole Kelvin. Okay, so I can plug this in, and I can get a value for delta G naught. And when I do this, I get that delta G naught is equal to 113 joules per mole, which is interesting, right? I'm going to write this down off to the side. What this tells us is that the reaction is not spontaneous under standard conditions. Now, we don't need that for this problem, but we are going to analyze the results of this problem in a bit. So this delta G naught now is the only thing that we need to calculate K. So I'm going to use 300 Kelvin here. I'm going to use my 8.315 there. I'm going to use my unrounded delta G naught there. Okay. So what I can do for this is I can calculate a K. And again, please check my math. And what I have is 0.95571 is equal to K. So at this temperature of 300 Kelvin, this is the equilibrium constant. For this reaction, all right, this is the equilibrium constant we would give you. All right, and you've just been given this, but now we see how we can calculate it. Okay, but wait a second. What is delta G naught then telling me? Well, remember, delta G naught gives you information, right, under standard conditions. Delta G naught gives you your K. This is a K for this reaction. K for sure, no matter what, is 0.95571. No matter what, that's the K for this reaction. A gas going to B gas. Now check this out. We know the reaction is not spontaneous under standard conditions because we got a positive delta G naught. I'm going to prove that in a different way, that the reaction is not spontaneous under standard conditions. In fact, if it's not spontaneous under standard conditions, you get a positive value. What does that mean? That means that the reaction is actually going to progress in this direction under standard conditions. Well, hold on a second. What's Q under standard conditions? Here's this reaction. What I would be doing is I would be looking at the concentration or pressure. Let's do concentration. Let's make arguments for concentration. Concentration of B, right, initially, over the concentration of A, initially, right? We can build a Q and a K expression, right? K, this is your concentration of B at equilibrium and your concentration of A at equilibrium. We can make pressure arguments. Remember, there's a relationship between Kp and Kc. It's the same idea here, though, right? Hold on a second. Under standard conditions, you know that this concentration is 1 molar. That's a definition. Under standard conditions, you know that that concentration is 1 molar. Under standard conditions, and this is an important concept and we'll reinforce it in the next video, but it's important right now, just analyzing this. Under standard conditions, Q is equal to 1. Every single time, Q is equal to 1. Well, hold on a second, right? How does Q compare to K? This is our K no matter what. No matter what the conditions are, this is always K, right? Q is greater than K, all right? For this particular reaction with a positive delta G naught, my Q is 1 and my K is 0.955, which is bigger. Q is bigger than K. This is why we made that rule earlier in the semester. When Q is bigger than K, which way does the reaction progress? It progresses towards the reactant side, right? I'm going to link this all up one more time because it's incredibly important, okay? We did a thermodynamic analysis and we got a positive delta G naught. That means that the reaction is not spontaneous, and it actually means that the reverse reaction is spontaneous. Our delta G naught can give us a K, and this is the value of K that we get, okay? This is the same equilibrium constant we've been analyzing all semester. We are under standard conditions, so we know that Q is equal to 1. Because every pressure inside here we would replace with 1, and every concentration inside here we would replace with 1 due to the definition of standard conditions that we went over in our first video this week. If I look at how Q and K compare, Q is definitely bigger than K in this situation. So guess what? Via this number, predicting the reverse is spontaneous, and via this comparison that Q is bigger than K, meaning that all semester when Q was bigger than K, which way did the equilibrium go? It went towards the left, right? We see that at equilibrium, right, with initial starting conditions that are standard, you will have more A and less B, right? A lot of connections to make. Rewatch this as much as you need. This only applies under standard conditions, all this analysis that we did. Now, K always comes from a delta G naught, but what happens if we're not under standard conditions? That's what we're going to explore next time, okay? So everything we've talked about this time applies for standard conditions. Next time we explore non-standard conditions.